All right, our topic today is looking at rational functions. Mostly all that we're doing is looking at asymptotes today. We have to consider vertical and horizontal asymptotes. So we've already done, from our curve sketching unit, we've already talked about critical points, we've already talked about inflection points and our intervals of increase and decrease. This is really the only thing left to talk about is end behaviors and asymptotic behaviors, which a lot of it you've seen before. So we're going to talk about this. I'm going to explain horizontal asymptotes, I think, a little bit differently than you would have seen them previously. We want to take a little bit more of a limit approach to things. But otherwise, I think a lot of what you're going to see today should be similar to what you've done before. Yeah, not too much new there, right? Just horizontal, vertical. Let's move along. Vertical asymptotes are easier. The reason we get vertical asymptotes with rational functions is because we can't allow the denominator to be 0. And that's the only reason we get a vertical asymptote. It's all about the denominator. The numerator actually makes no difference at all to the location of an asymptote, vertical asymptote. So this is the function we're used to, that 1 over x graph. We even have seen that back in the grade 11 course. And we're going to talk quite a bit about this one to base our other ideas out of. So just some of the notation here that I've got written. We're considering what happens right around that vertical asymptote. The vertical asymptote occurs at x equals 0. So if we're getting close to 0 from the left, and remember that's what that negative sign there means, right? As x is approaching 0 from the left-hand side. So as we're coming in this way, what happens to the function? Well, the numerator stays as 1, right? Nothing we can do about that. But the denominator becomes a very small negative number. And we have to be careful today because we have to talk about the idea of small and large numbers. And we're also going to talk about negative and positive. So when I say small, we're going to think of numbers like 0.1, 0.001, 0.0001. That'll be a small number. Okay. Then I say negative, which means I'm putting a negative sign on it. Okay. Technically, if we just want to talk really small numbers, you could argue that, you know, a really small number is negative 1,000, which is true, right? It's more negative than other numbers. So that's our issue today. We're going to have to be a little bit careful. I'll do my best. A small number will be a number close to 0, okay? A large number will be obviously a large number. And then we're going to talk about it either being negative or positive. So in this case here, I have 1 divided by a very small but negative number. If we just think about the 1 divided by a small number for a second, ignore the negative. If I go 1 divided by a very, very small number, I should get a very, very big number, right? 1 divided by 0.000001 is a really, really big number. But then I'm also tossing in the fact that it's a negative number. So it's 1 divided by a small number becomes a large number, becomes a large negative number. And we say that overall, this approaches negative infinity, which is exactly what we see in the graph, right? It's on its way down. Similarly, as we approach 0 from the right, we're now a small but positive number. So 1 divided by a small number is a very large number, and it's positive, and therefore the graph is approaching positive infinity, which is what we see as we approach 0 from the right. Okay? That's one we're used to. Here's one that's a little bit different. Pretty good function, actually. We've got a quadratic on the top and a quadratic on the bottom. It says sketch the graph of the function around its vertical asymptotes. And all I care about today is how things are behaving around the asymptotes. So this is not going to be a complete curve sketching exercise. We'll do more of that in the days to come. All we want to focus on is what happens around the asymptotes. And if I want to look at the vertical asymptotes, I need to consider the denominator. And I need to factor it. So I'll factor it as x plus 3x minus 2. That says that x is equal to negative 3, or I should say x can't be negative 3, and x can't be 2. Those are the two restrictions on this expression, which means that our vertical asymptotes are at x equals negative 3 and x equals 2. That's where we're going to see them. Now notice the difference in the way I've written things. When I wrote the function down, I said x can't be negative 3 and x can't be 2. And in the green there, I said the vertical asymptotes are x equals -3 and x equals 2. The distinction there, the red is the function itself, right? The function, if I was actually going to graph that, x can never be -3 or positive 2. The vertical asymptotes are our two vertical lines. They aren't actually part of the function. We usually draw them in with our dotted lines, but they aren't actually part of the function. So here's my little sketch. This is where the asymptotes will go. 1 at x equals -3, and 1 at x equals 2. Now, there's still different possibilities of what might happen on either side of those functions. And that's what we have to look at now. We're wondering, does the graph look like that, or does it look like that? And same thing on the other sides, right? We have to look at all of those possibilities on both sides of both asymptotes. So let's consider that x equals -3 at first. What happens as x approaches -3 from the left-hand side? So if we're coming in close to -3, but we're approaching it from to the left of -3. So an example number there would be -3.001. Right? That's to the left of -3. What I'm wondering is, what happens to the function? So my function was x squared plus 1 over x plus 3, x minus 2. And so if I sub a number in like -3.001, and this is, I don't have to sub in exactly that, but this will give us an idea of what's happening. If you consider subbing in a number like that, the number on the top, x squared plus 1, is going to be around 10, right? The x squared is going to be a little bit bigger than 9, plus 1 is going to be a little bit bigger than 10. I'm going to put a approximately equals 2 there. This isn't exactly right, but it's close. With the two brackets on the bottom, the bracket on the right, the x minus 2, that's going to turn out to be around -5. Those really aren't the important numbers. What's important is the first bracket there, the x plus 3. It's going to be really, really close to 0, right? -3.01 plus 3. The important part, though, is since we're approaching from the left, that's a really small number, but it's a small negative number. And that's what I'm going to put in here. It's a small negative number. Because the important thing to realize here, I really don't care what number I get when we do this. All we're interested in is where this graph is going. Is it approaching positive infinity, or is it approaching negative infinity? I know it's one or the other. I just have to care if it's positive or negative or not. Well, the top is 10, so that's a positive on the top. On the bottom, I have a small negative times -5. So a negative times a negative would be a positive on the bottom. That means I have positives all over the place. So this has to be a positive answer. And notice, since this is a small negative here, the whole bottom is a really small number, right? So our numerator is 10. That's comparatively large. And we're going to have a very, very small denominator, getting smaller and smaller, right? As this number gets closer to 3. So a large positive on the top, a small positive on the bottom. This thing is going to be approaching positive infinity as x approaches -3 from the left. What about as we approach -3 from the right? I don't even care. I don't care about these numbers again, right? What's happening? Well, the top is still going to be a positive number, isn't it? In fact, it's always positive. X squared plus 1's got to be positive. The x minus 2, the second bracket's a negative number because I'm getting close to -3. And now, that x plus 3 part, remember an example for this, getting close to -3 from the right, an example would be something like -2.99. So that x plus 3 should now be a small positive. And so if you think about that whole thing, I have a large positive number on the top. a positive times a negative on the bottom, so a negative on the bottom, and it's really small. So a large positive divided by a small negative is going to be going to negative infinity. And I can put that on the graph. The first one, as we approach negative 3 from the left, the graph's going up like that. And as we approach negative 3 from the right, the graph's going down like that. And I don't know what's happening to the left or to the right. We're not worried about that, right? All this said was to sketch it around the asymptotes, and I've done that. We're showing what the behavior is at those parts. Okay, for sake of space, I'm going to just erase part of this. I hope that's okay. Pause it if you need to copy some stuff down there still, because I want to go on to the 2 part. Just get rid of that. So what if we approach 2 from the left? And then down here will be 2 from the right. Well, as we approach 2 from the left, what happens to this function? The top is still positive, right? X squared plus 1, that's going to be close to 5. The bottom, the x plus 3 is going to be close to 5 too, isn't it? It's going to be just a little bit less than 5 because we're approaching 2 from the left. But it's a positive number, that's all that I really care about there. And then what about the x minus 2? Well, it might help to think of our example again. We're approaching 2 from the left. So we need a number just a little bit left of 2, which would be 1.99. If I went 1.999, take away 2, I'm getting a small negative number there, right? So large positive on the top, divided by small negative on the bottom. That graph's going to negative infinity, so it'll look like that. And then what happens on the right of 2? Oh. To the right of 2, well, I still have a large positive on the top. X plus 3 is still close to 5, so that's a positive number. And now the x minus 2, that should be a really small but positive number. So everything's positive, but it's a large divided by a small. So this one's approaching positive infinity. So as we get close to x equals 2, we're going up to positive infinity as we approach that asymptote. That's how we handle vertical asymptotes, okay? And one of the questions I guess that gets asked for this unit, how much do I have to show? You're pretty much showing stuff like this, okay? You got to give me some indication that you're understanding what's happening around the asymptote. It isn't enough to not write anything down for this. And as I get the solutions posted for the homework questions and stuff that we'll do this unit, you'll see a little bit more what I'm expecting for this. So you can't just assume all this stuff. You're gonna have to show me the work for it. Okay? There's vertical asymptotes. Horizontal is our next one. And the horizontal we have to be a little bit more careful with, because there's more things influencing it. It's not just the denominator anymore. The numerator and the denominator both play roles. So going back to that 1 over x graph, because that's the one we're familiar with, we know that it has a horizontal asymptote at y equals 0. So if we consider sort of the possibilities, there can only ever be one horizontal asymptote, right? That's good news for us. What we need to consider is just what's happening as we go all the way to the left and all the way to the right. So for the first one here, as x goes to positive infinity, we're getting larger and larger and larger. What happens? Well, the 1 stays on the top. There's nothing you can do about that. It's just 1. But on the bottom, we now have a really, really big positive number. And 1 divided by a really big number means you're getting closer and closer to 0, right? 1 divided by 1,000,000 is really small. 1 divided by 1,000,000,000,000 is even smaller. You're getting closer and closer to 0. And since everything was positive, it says we're approaching 0 from above, because it's getting closer and closer to 0, but it's always positive. That's why we're approaching it from above. So we're getting closer and closer to this horizontal asymptote, but we're getting closer to it from above the asymptote. If we go to the left, if we're approaching negative infinity, the same sort of thing happens. We still have a very large number on the bottom, but now it's negative. So 1 divided by a large number gets close to 0, but because it's negative, we say it's approaching from below, because this expression is always going to be negative as x gets closer and closer to negative infinity. Okay? So what would happen here? Determine the horizontal asymptotes, if any, for each of the following rational functions. Let me get rid of these ones for a second, so I have a little more space. And some of this you might remember from advanced functions. Right? You might remember some of the rules, and that's good. Rules are good. But I want to make sure we understand why everything's happening. One thing to remember, and I just mentioned this, there can only ever be one horizontal asymptote, right? So if I go to the right and discover that there's a horizontal asymptote as x approaches positive infinity, it's the same horizontal asymptote if we approach negative infinity. Okay, so that part can't change. So what I'm going to do for this is I'm just going to say what happens as x gets really, really big. And that'll give us the idea. I'm going to pick a test point. So I'm going to say let x be, well, 1,000 doesn't seem too big, but it's actually one that we can handle relatively easily. So if x is 1,000, what's y? It'll be 1,000 on the top, and on the bottom, it'll be 1,000 squared plus 1. Now, do we need to pull out our calculator for that? Because what we're interested in is there a horizontal asymptote, right? Is this approaching something? And I think, I don't think we actually care what the number is. I can tell you, heck, you guys usually like numbers if I recall classes from before. Divided by, okay, the answer I get is 0.0009999, lots of 9s. Really small number, right? Really small number. What's it getting closer and closer to? It's getting closer and closer to 0. I think that makes sense because the number on the top appears big. It's 1,000, right? That seems like a large number. But the number on the bottom is bigger. And if x gets, if we're letting x approach positive infinity, that denominator is always getting bigger, right? The x squared is going to get larger quicker than the x term. Right? The x squared dominates the x. So our denominator is getting bigger faster than the numerator is. And because that's happening, we're getting closer and closer to 0. So as x approaches positive infinity, y is approaching 0. Okay. Now, granted, I haven't talked here about if we're approaching from above or below. Here, I guess you can tell, right? We subbed in the 1,000, and that number is positive. So we're approaching the asymptote from above. If I was going to sub in negative 1,000, the denominator would have been a negative number, right? So we would have been approaching from below. What's really important for me there, though, the asymptote is y equals 0. So our horizontal asymptote was y equals 0 for that example. How about this one? X cubed plus 4. What's going to happen there? On this one, think about what happens if you sub in a big number. I'm not even going to pick a number this time. What happens if you sub in something really big? The top is a big number cubed plus 4, and who cares about plus 4? And on the bottom, it's just a big number. And that number is going to keep getting larger and larger and larger, right? So what dominates here is the x cubed, right? The larger degree always dominates over that linear term, the x. So what this is approaching is a really large number. Part A example, we were getting closer and closer to 0, right? This time, this expression is getting larger forever. Just keeps getting bigger and bigger and bigger. That means this one here has no horizontal asymptote. It just doesn't have one. if the numerator is larger, you can't approach an asymptote, right? It just keeps getting bigger and forever. Your graph would look something like, the one side is going to look something like that. In fact, it's going to look something like that on the other side too. So there's no horizontal asymptote going on at all here. I think I need a little bit more space. Let's pull out part C. This one's a little bit bigger. 5x squared plus 2x minus 3. But all I care about is there a horizontal asymptote or not? Or not. So what happens if we sub in a number that's really big? Well, on the top, this 5x squared is going to make things very large, right? The 2x is going to contribute a little bit. The minus 3 isn't going to do much. What's important is that 5x squared. It's the biggest degree. It's going to make things on the top very large. But on the bottom, you got an x to the 5th. And the x to the 5th spokes the x squared, right? X squared thinks it's getting big fast, and the x to the 5th says, you got to be kidding me. This is really, really big. So that means, comparatively speaking, I have a small number on the top and a really large number on the bottom. That's going to get really, really close to a small number. Gets really, really close to 0. So y equals 0 is your horizontal asymptote. I think that makes sense, right? Really small, comparatively small number on the top, very large number on the bottom. A small divided by a large gets closer and closer to 0 each time, okay? Here's our note, and this helps us sort of summarize what's going on here. It says if the degree of the if the degree of the denominator is greater than the degree of the numerator, and that's what we see in this example, right? The degree of the denominator is 5, the degree of the numerator is 2. If that happens, then the top gets big, the bottom gets bigger, so we end up with a horizontal asymptote of y equals 0. If we have things the other way around, like example B there, if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. No horizontal asymptote there at all. We still have to wonder, I suppose, if we're going to be approaching, if going up to positive infinity, if we're going down to negative infinity, but there isn't an asymptote there. Okay, that takes care of two cases, right? What if the degree on the top is bigger, or what if the degree on the bottom is bigger? What it doesn't take care of is what happens if the degree is the same. If the degree is the same, then there will be a horizontal asymptote, but it's not going to happen at y equals 0. It's going to happen somewhere else. This is the part where I'm pretty sure you were told a shortcut in the advanced functions course to figure out where the horizontal asymptote is. So you might be looking at that one already going, I know this one, I know what the horizontal asymptote is. My guess is you figured it out based on some trial and error. You did a few examples and you said, oh, look, this is what must be happening. So what I want to show you is how we can show, with limit ideas, what the horizontal asymptote actually is. So we're going to take this expression, the y equals 3x squared and so on, and actually figure out exactly what the horizontal asymptote is. And it's kind of weird. So I've got the steps here. I don't think you've really done steps like this often. So step number 1, common factor out the largest degree. Remember, what I'm wondering is what happens as x gets really, really big. Okay, what happens if I sub in a really, really big number? And in this case, the top and the bottom are both getting big at the same rate because the x squareds dominate on the top and the bottom. Okay, so how does that balance out? Common factor the largest degree, it says, is the first step. So the largest degree is x squared, right? There's an x squared, and that's the largest degree. That means that I'm telling you I have to factor out x squared from the top and bottom. That's weird because if I said to you common factor the top, 3x squared plus 2x minus 5, you'd say I can't. we'd look at that and say, I don't know how to common factor that. We can common factor things. Oops, it's really bad writing. We can common factor things that look like this. Right? That you can common factor. That works because you'd look at it and say, well, 3 goes into both 3 and 6, and x goes into both x squared and x. Here, 3x squared plus 2x minus 5, there's nothing common there. So I'm forcing your hand. I'm saying no matter what, you have to factor out an x squared. Okay? That's not too bad for the first one, because there's a 3x squared and we factored an x squared out. There's still a 3. But what happens for this next one? Well, what's the next term in the bracket? Well, to help, look back at this red one that I did. Remember, common factoring is the opposite of expanding, right? 3x times x gives me 3x squared, and 3x times 2 gives me 6x. So what do I need to put here so that when I multiply it by x squared, I end up with 2x? Well, I'm going to need a 2 for sure, right? So I'm going to have a 2. The other thing that I'm going to need is I'm going to need an x in the denominator. So it looks like this, 2 over x. And take a look at that for a second. I think you can see why it's going to work. X squared times 2 over x. The 2 will stay. The x on the bottom cancels with one of the x's, and we're left with just 1x on the top. So we get 2x. How about the next one then? The same idea should apply, I think, right? We need something times x squared to get minus 5. No, it better be a negative. And I need to completely cancel those x squareds. So we put an x squared right there. X squared times minus 5 over x squared. The x squareds cancel and you're left with just the minus 5. See if you can get the bottom then. We're factoring out an x squared. If I factor it out from the first one, there's a 1 there, right? So 1 plus 1 over x plus 7 over x squared. Kind of weird math, right? It looks horrible now. We've created these extra fractions where we really didn't want them. But it turns out it works. It's going to work for our purposes. The advantage is now we factored out an x squared from both. And so if you have an x squared here and an x squared here, those can cancel. And we're left with just that. Okay, so only those brackets really remain. I'm going to slide step 2 there. Step 2 focuses on what we mentioned before with the 1 over x graph. We know that if x is approaching a really big number, then 1 over x gets closer and closer to 0. So I'm going to write this down again. Y equals there we go. Now what happens, because I'm interested in our horizontal asymptotes, right? What happens as x approaches either plus or minus infinity? What happens as x gets really, really big positive or really, really big negative? I know that 1 over x approaches 0, right? So what happens to this function here? Y is now going to approach. Well, I'm just looking at the numerator for a minute, okay? It has a 3. So 3 doesn't have anything to do with x. What about this, though? 2 over x. As x gets really, really, really big, 2 over x gets really, really small, right? Approaches 0. So a 0 there. The second one, minus 5 over x squared, well, x is getting really, really big. So 5 over a really, really big number would be a number really close to 0. And technically it's a minus, but it's a 0, so it doesn't matter if it's plus or minus there. On the bottom, the 1 is still there. 1 over x gets really close to 0 because x is getting really, really big. 7 over x squared gets really, really close to 0. And so in the end, y is getting really, really close to 3. So the horizontal asymptote for this one is y equals 3. And that's how we can show it using the idea of a limit. What happens as x gets really, really close? Well, sorry. What happens as x gets really, really big? by dividing out that largest degree, we've created a whole bunch of mini rational functions inside things. And that's allowing a whole bunch of things to equal 0, or to approach 0, I should say. So that there is how we can demonstrate how to get a horizontal asymptote. So let's try this one. It says sketch the graph around the horizontal asymptote. So we're going to try and do a little bit better job. We're actually going to we'll get the asymptote, and we'll decide if we're approaching from above or below. Okay. So I want to take the same approach that we just did. What we said in the last one was notice the degrees are the same, right? X squared on the top, X squared on the bottom. If the degrees are different, then we know what happens. If the degree on the top is bigger, there's no asymptote. If the degree on the bottom is bigger, then we know there's a horizontal asymptote at y equals 0. Here we don't know. So, here you might know. This is how we're going to show it. So we're going to common factor the highest degree. Highest degree was the x squared. What does that leave us with if we do it? Well, there's a minus 6. And then the plus 4, we had to take an x squared out of it. So that's 4 over x squared. On the bottom, factored in an x squared, that'll leave us with a 3 and a plus 2 over x. So the reason this works, x squared and x squared were pulled out. They cancel. You're left with minus 6 plus 4 over x squared and 3 plus 2 over x. And what happens as x gets really big? Well, as x gets really big, I should probably write that over here, shouldn't I? As x gets really big, y is going to be a minus 6 plus 4 over x squared. That's going to be 0, right? 4 divided by a really, really big number. And then 3 plus 0. So our horizontal asymptote is y equals minus 2. That's good. We know what our asymptote is. Here's a little sketch. Remember, just a sketch. That's all we're doing here. And at y equals minus 2, there's my horizontal asymptote. Now, what I'm still wondering then is, as we go out to positive and negative infinity, is the graph going to be doing this, or is the graph going to be doing this? And I need to know that on both sides, right? As we approach negative infinity and as we approach positive infinity. There's different ways to do this, but in the end, I've sort of decided that really I'm just happy doing test points, which isn't exciting, and it disappoints me that it's not exciting. As I check in behavior, what happens if x is 1,000? And what happens if x is negative 1,000? What happens as we sub those in? What I care about is the number that I get. Is it bigger than negative 2 or less than negative 2? So this is a case where the number matters, right? I'm going to have to actually calculate this a little bit more carefully, because I need to know. Oops, of course, now I erase my function. Shoot, where did it go? Let's bring this guy down here so I can see him. I need to know. I need to be able to compare my answer to negative 2. So if I sub in 1,000, minus 6 times 1,000 squared plus 4. And be careful putting this in your calculator. You can do it, but just be careful. It should come out really close to minus 2. If it doesn't, you know you've made a mistake. got minus 1.9986, lots of sixes. What's important is that that number is actually a little bit above minus 2, right? So this is approaching our horizontal asymptote of y equals minus 2 from above. It's a little bit bigger than minus 2. So if I go back to my graph on the top right here, as x gets really, really big, as x gets close to, well, I've got 1,000, right? As x approaches positive infinity, the graph is approaching that horizontal asymptote from above. And I don't know what else is happening in the middle there, but I know at the end, it's approaching from above. If I put in minus 1,000, what does that do? It's not going to change too much, right? Those two squared values still just turn into positives anyway. And with this one, I got minus 2.00133 and so on. And what's significant about that is that that's a little bit below minus 2. So here we're approaching the horizontal asymptote, which was y equals negative 2, from below it. So my graph's looking like that. And there's no guarantee that if one approaches from above, the other one has to approach from below. Okay, that doesn't have to happen. It often happens, but doesn't have to. So this is something that we need to check each time, just to make sure. Okay, there's quite a lot there for us to be able to check. These asymptotes. And again, all we've really done is we're just looking at end behavior here with the horizontal asymptotes. And with the vertical asymptotes, we're just considering what happens right around those. But we're missing lots, right? All of this stuff in the middle, we didn't talk about what's going on there. So in the next while, we have to consider all those possibilities still. What happens if we put our asymptotes together with our critical points and with our inflection points? So coming up will be examples where we do everything. The whole curve sketching algorithm. Technically now we've done all of the components, right? The components were y-intercept, x-intercept, critical points and intervals of increase, decrease, inflection points and intervals of concavity, vertical asymptotes and horizontal asymptotes. Those are the things that we need to do. We just haven't done any examples yet where we've done all of them at the same time. So that's what's coming up for us in the next few days.